I'll talk to you today about some of my work dealing with patterning various commercial nanofiltration and reverse osmosis membranes. And so why are we interested in this? If we have water purification membranes, my research has been focused on reducing and reversing membrane biofouling on all sorts of different types of membranes, so ultrafiltration, nanofiltration, and reverse osmosis membranes. And I've done this through two different techniques. The first being a pattern membrane, which I'm going to talk about today, and the second, a surface chemistry that we used, the special surface chemistry, which I have a talk Thursday about if you would like to attend that. And so why is this important? By reducing the fouling, we can reduce the energy costs associated with water treatment. When membranes get fouled, you build up a new layer of resistance, and thus to keep a constant flux, you have to increase your pressure. So if you don't have to increase that pressure, we have then saved money. And so how we have previously done this, and so we published a paper last year on this, is combining patterning with chemical coatings. And so we took some work based on what John Pellegrino has done in Colorado and kind of extended on that by applying this chemical coating. And we're able to show that when we combined both of those methods, we were able to reduce alginate fouling better than either method alone. And so we did this on a single nanofiltration membrane, and we're the first to show that you can actually directly pattern these membranes. And so that got me thinking, can we do this on others? And so I took 13 different commercial membranes that we purchased or received, and looked at all sorts of different chemistries. So you can see we have a typical RO-based chemistry or a typical nanofiltration-based chemistry. Most of them all have polysulfone support chemistry, but one does have a polyether sulfone. And when we pattern them, you notice we have kind of varying degrees all across the board. And so this has really kind of perplexed us as to why all of these are different. And so that led me to lead to the question, what causes our difference in our patternability? And so I looked at all sorts of different things that I assumed was part of the polyamide layer that might cause these differences. And so we looked at pristine surface roughness, we looked at contact angle and surface free energy, we looked at maybe Young's modulus of the top layer, we looked at the permeance and the rejection of these membranes, we also looked at the polyamide layer thickness, and none of these things correlated. Nothing seemed to correlate at all with how these membranes patterned. And so we got tipped at AIChE this past year to looking at the amount of glycerol that is present in the porous support. So not necessarily the polyamide layer, but the porous support underneath. And so there's been a lot of work recently showing that these porous supports act as open cell phones under these compressions. And so we were interested in looking at this model and seeing if maybe with the yield strength of these membranes might change with the glycerol content. And so this P star here is our effective membrane density. And so these are porous. If you imagine they're part air, right? And so if you fill it with glycerol, you can then change some of that density that is present in these membranes. And so we wondered if playing with that might be the key, because we don't know what exact humectant or pore filler is used in these membranes, and we don't know what concentration they're used. So if we uniform that, maybe we have an idea. And so when we did this, we looked at, so patterned as received was the previous data that I showed before, just in a different graph. And then I rinsed out all of the pore filler, and then I filled it specifically with glycerol in a 15 weight % solution and let that dry. And then I patterned it. And so the important thing here is to look at the different chemistries as themselves, as subsets. So if we first look at the MPD-TMC chemistry here, we had quite a range going on, and then when I filled it with the 15 weight glycerol, that came down a little more. So it became more uniform, not perfect, but still more uniform. And within the air, they're all considered the same. When we look at the piperazine-based membranes, again, they became more uniform. There are a few more differences with that. That may be due to the uptake of glycerol in each of these membranes. We're not 100% sure of that with that. I also looked at patterning a couple supports as well and seeing how do they kind of factor into this similar glycerol thing, since that's what we're basing this on, is these porous supports present. And they seem to be shipped about the same as what I ended up patterning them with. So I have done some preliminary studies to look at if we vary the glycerol content, can we fit into this model? And the answer is no, not at the moment. I've looked at an MPD chemistry, I've looked at a piperazine chemistry, I've even looked at it based on a support to see can we fit this model to varying the glycerol content and thus varying the effective density. And there's no trend at the moment. So I do not have a great answer for this, and so if anybody has any suggestions, I would be happy to take them. So with that, I would like to acknowledge the acknowledgements and thank you for listening.